Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our first set of notes over chapters 15 and 16, and we're looking at solutions. So this is our solutions chapter, and in the next two chapters we're going to be talking about solutions and energies in reactions. Now, a solution, if you recall from first semester, is a homogeneous mixture containing two or more substances. And the term solution is actually a synonym for the term homogeneous mixture. So they're interchangeable with each other. So when you have a homogeneous mixture, remember that's a uniform mixture. So anytime we have a situation where a substance dissolves in another substance to make a homogeneous mixture, we have what we call a solution. Now, you may recall from middle school and elementary science that the solvent is the substance that does the dissolving in the solution. And one of the problems with that definition is in many situations, there's no way to really look at what's there and determine what actually does the dissolving. So we're going to look at a more simplistic definition of solvent. Think of the solvent as the substance that's there in greater quantity. So whatever we have there in greater quantity is going to be the dissolving medium. And what gets dissolved, which you may remember from middle school, is called the solute. Well, that would then be the substance that's there in lesser quantity. So when we talk about solutes and solvents in chemistry, remember the solvent is always what's going to be there in greater quantity. The solute is what's going to be there in lesser quantity. Now, solutions may be gaseous or liquids or solids. And really the state of the solution depends upon the state of the solvent. So the thing that's there in greater quality, quantity, is it a solid, liquid, or gas? And that's going to determine whether we call the solution or refer to the solution as a gaseous, liquid, or solid solution. Now, what are different types of those solutions? Well, braces would be a good example of a solid solution. You have metals that are blended together. So you've got nickel, which is there in greater quantity, so that would be our solvent. And mixed in with that nickel is titanium. So we've made an alloy of nickel and titanium. Well, it is a homogeneous mixture of those metals, so it's a solution of those metals. Gaseous, that would be something like air, a solution of gases mixed together. Now, in air, 80% of air is nitrogen gas, N2, so that would be the substance in greater quantity. So in air, nitrogen would be the solvent. And one of the primary solutes that would be in air would be oxygen, O2 gas. Now we exhale a little bit of carbon dioxide and there's other trace gases that are there. Those would all be examples of solutes inside the gaseous substance, which in this case would be the nitrogen. Now, most of the time we're going to be dealing in this chapter with liquid solutions, and in particular, liquid solutions where water is the solvent. So we're going to be referring to and using a lot in this chapter liquid solutions. So when you take salt and dissolve in water, dissolve Kool-Aid in water with a little bit of sugar, our solvent would be the water. So it is a liquid solution because our solvent is water, a liquid. Now, simply putting two substances together doesn't really guarantee that you're going to make a solution. One must dissolve in the other. And some combinations will do this readily, and others won't do it at all. And there's vocabulary words that are tied to these ideas. If a solute does dissolve in the solvent, then we refer to the solute as soluble within the solvent. So something that's water soluble means our solvent is water, and our solute is dissolving in the water. And a good example of that would be sugar and water. Pour some sugar in water, stir it around, and the sugar dissolves within the water. So we say it's water soluble. Now, if it does not dissolve in the solvent, then we refer to it as insoluble. Good example of that would be sand is insoluble in water. Put sand in water, you can stir it all you want, and it doesn't appear that the sand dissolves. Now, one thing that I do want to mention in relation to the term insoluble here, typically what we're really doing is we're saying something is insoluble, and that's because its solubility is so incredibly low. To some small degree, sand probably will interact with water, but it's a very, very, very small amount. So for all intents and purposes, we would say sand is insoluble in the water. And what we really mean is insoluble is it's so small it might as well be zero. It's negligible. Now, an example of two things that when you mix them together, they don't mix like sand and water. Another example of that would be oil and water in the case of salad dressing. So in certain types of salad dressing, you have to shake them up because you have got an oil layer and a water layer that have separated. Now, in elementary and middle school, sometimes teachers will talk about this and they'll say they don't mix because the difference is in density. Well, that's not at all true. Oil is floating on top because of its density being less than water. But the reason they mix or don't mix doesn't have anything to do with density. It has everything to do with the types of interactions that exist between the particles. And we've already talked about this in a previous chapter. We got into polar and nonpolar molecules. So that's something we're going to come back to. Now, in this case, what we're looking at is two liquids that don't mix together. Now, there is a special name for when liquids are insoluble, and that's immiscible. So two insoluble liquids combined would be an immiscible mixture. Now, on the flip side, we can actually have liquids that mix in any proportions, and those things would be determined miscible liquids. Remember, we're only talking about liquids blending or not blending here. So a good example, that would be isopropyl alcohol. Rubbing alcohol is typically about 99% alcohol and 1% water. Well, if I dumped in a whole bunch of water and made it 99% water, 1% rubbing alcohol, it would still be a soluble situation. They would still dissolve in each other. So they mix in any proportion, so they're termed miscible liquids. Now, how come some substances are soluble while others aren't? Well, we've got to go back in time to in first semester when we talked about intermolecular force. So it really deals with the attractive forces at work between the particles. And you need to remember, solute particles are attracted to each other. Liquid or solvent particles, in the case of water, that would be liquid water molecules, are attracted to each other. And then when things dissolve, the solute is attracted to the solvent. So we really have three different types of attractions we're looking at when something dissolves or doesn't dissolve. So in order for something to dissolve in something else, the attractive forces between the solvent and solvent, or solvent and solute, must be strong enough to overcome the attractive forces between the solute particles to each other and the solvent particles to each other. So there needs to be a strong enough interaction between the two in order for the dissolving to occur. So if you look at an ionic substance in this case, what we're really looking at is if this ionic solute is dissolved in the water, what's happening at the particle level is there's attractions that are forming between the water molecules and the cations and the anions that exist when they get surrounded or dissolved by the water molecules. So in this particular case, water, if you recall, is polar. It has positive and negative regions. And ionic compounds are made up of cations and anions, definitely positive and negative things. So there's an attraction that can exist between the polar water molecules and the ions that are here. And if that attraction is strong enough, it can overcome the attractions of the original substances to themselves, and you end up with the dissolving situation. Now, as a general rule, what we refer to the solubility rule as is like dissolves like. And what we really mean is polar solvents will dissolve in, or I should say polar solutes will dissolve in polar solvents, as well as nonpolar solutes will dissolve in nonpolar substances. So that's really what we mean when we say like dissolves like. What we're referring to is the polarities that exist between the substances. And if they're both polar, then they're going to be attracted to each other. If they're both nonpolar, they're going to be attracted to each other and they'll mix. But if you put together polar with nonpolar, there's no attraction between the two that are strong enough. There's no attraction between the two that are strong enough to make the particles dissolve. So we have two polar things in top, and the red represents areas of polarity here, and the yellow and gray represents areas of non-polarity in the bottom. So when we have that top situation, we have a polar attraction between the two substances, and therefore they're going to dissolve. In the bottom situation, we have two nonpolar substances which both have London forces to each other, and they're going to interact. And what's really happening here is the attractions are strong enough to overcome the old attractions that existed, and they dissolved. Well, if we had polar with nonpolar, the new attractions are almost non-existent between polar and nonpolar, so there isn't going to be attractions between the two. Now, the general process of dissolving we refer to as solvation, the surrounding of a solute particle by the solvent particles to form a solution. Now, one particular type of solvation we're often interested in is when our water is our solvent. We refer to that solvation process as hydration. And you can see in the picture here our cations and anions are being surrounded by water molecules. And you'll notice also, remember we talked about this when we talked about the polarity of water on the air, the oxygen side of the water molecule is slightly negative. The hydrogen side is slightly positive. And that explains why the hydrogen side orientates towards the negative chloride ions and the oxygen side of the molecule orientates towards the positive sodium ions. So this is what's happening at the particle level when we look at hydration. Now, when we have an ionic compound, which is what really just looked at as an ionic compound dissolving, ionic compounds are often soluble because the positive and negative halves of the water molecule can attract those ions. And that's exactly what we saw in the previous case. So when you have cations and anions, water molecules have slightly positive and slightly negative regions that can be attracted to those things. But remember, the attraction has to be strong enough. And what can happen with some types of ionic compounds, like calcium carbonate, the actual ionic compound, which I'm going to circle here, has attractions that are so strong the water molecule isn't strong enough to break them apart and dissolve them. So limestone, which is calcium carbonate, the attractions between the calcium and the carbonate are so strong the water molecule isn't strong enough to break it apart, and that's a type of ionic compound that doesn't dissolve. But many ionic compounds are held together weakly enough that the water molecules are strong enough to dissolve them. And this goes back to a like dissolving like type situation. So when we have an ionic compound, it used to be that the cations and anions were associated with each other. And when they're dissolving, they're breaking apart. They're dissociating. So a lot of times when we're referring to the solvation of an ionic compound, we'll talk about it as dissociation. The solid no longer exists as a well-ordered group. And the water molecule have pulled off the ions and surrounded them. And that actually stabilizes the process because distance kills attractive forces. And if these positives and these negatives are close enough together, then they will reassociate and reform the ionic substance. But the water molecules that you see in between the two, the hydration that exists around those anions and cations, actually stabilizes the ions as a hydrated ion and prevents them from recombining. So the water molecules surrounding the ions actually stabilize them and help prevent the recrystallization of the solid in the solution. Now, the process by which charged particles in ionic solids separate from one another, that's known as dissociation. So this is another way to refer to solvation, basically. Now, water molecules actually make a pretty good solvent because as a substance with partially positive and partially negative regions, there's a wide variety of both molecular things as well as ionic things that will be attracted to them. A good example of that would be something like table sugar. Now, table sugar or sucrose has a lot of OHs on them, and you can see them circled here in the picture. And those OHs form a hydrogen bond. Now, remember, hydrogen bond isn't the bond between the oxygen and the hydrogen. It's the strongly polar situation that exists with the very negative oxygen and the very positive exposed nucleus to the hydrogen when the electron shifts away from it. And what that does is it will attract very strongly to water molecules that are nearby, which also display this hydrogen bonding situation. So that hydrogen and that oxygen will form a strong attraction between the two, and that's what hydrogen bonding really is. So it's not within the covalent bond itself, it's the bond between molecules. Remember, it's an intermolecular force. Well, all those OH bonds all over that sugar molecule are sites of hydrogen bonding to water molecules, so they readily hydrate. And those water molecules can then pull off that crystal from the crystal lattice, surround it, and hydrate it, and you end up with dissolving. So water molecules can not only dissolve ionic substances in many cases, but they will also dissolve in other polar molecules. And you can see here all the waters that are attracted to that hydrogen bonding that exists between the OH in the water and the OH in the sugar molecules. Now, not all things dissolve like each other, and some things will dissolve faster than the others. So what we're talking about is how quickly something happens, that's a rate. So like our car has a rate of travel, how fast it changes its location, then we can also look at how fast a substance dissolves. Now, in order for solvation to occur, solute molecules must be separated and surrounded. And remember, that takes time, and all those attractions aren't always equal to each other. So this can happen at different speeds, but fundamentally, it's going to start with an interaction between the two particles themselves. So this is going to happen through collisions between the molecules of the solute and the molecules of the solvent. And anything that we can do to increase those collisions or make them stronger is going to increase the rate of solvation. One simple example of that most people underrate is the process of mixing. When you stir a substance, you're basically moving the particles around. And what happens is when the water molecules hydrate the ions or the molecules that it's dissolving, then you end up with a very dense substance that just kind of clumps and sits there on the bottom. And not, yes, they're as a liquid, they're in constant motion, but that doesn't mean they're necessarily moving very far. Well, when we stir, we push them out of the way and bring in fresh water behind it to increase the rate at which the solvation occurs. So we move those other particles out of the way that have already been hydrated and bring in fresh water to hydrate more, and we dramatically increase the rate of the solvation. So mixing is hugely important to the dissolving process. And most people underrate it because you just naturally do it. You throw something in something and you stir it. Well, if you don't, it can take forever, and I mean sometimes decades, for things to dissolve without mixing. Now, another thing we can do to increase the number of collisions that exist between the two is increase the surface area. So if we take a large chunk and we break it apart into its pieces, now all the way around each of these pieces, we can get water that comes in and interacts, and we can get dissolving that's going to occur at more places. So increasing the surface area by breaking a large particle up into smaller particles can increase our rate of dissolving dramatically. And the last thing would be heating. If you increase the kinetic energy of the particles, they're moving faster. So as they dissolve, they're moving in and moving out at a quicker rate. And that's going to give you more collisions and allow more things to move more quickly through. So heating the substance can allow us to dissolve at a faster rate. Now, one of the things that is an important part of dissolving that I want you to understand, and this is going to set up some of the discussion we have in chapter 16 where we get into energy, is dealing with the heat involved in dissolving, or the energy involved in dissolving. That's called the heat of solution. In order to dissolve, we basically have to overcome the attractive forces that currently exist between the solvents to each other and the solutes to each other. And then we're going to form new attractions between the solute and the solvent that didn't exist before. So we're breaking old types of attractions and making new types of attractions. And this making and breaking involving energy is something that we're going to use a lot in chapter 16. So what you need to fundamentally understand here is to break apart bonds, that requires energy. And the term for a chemical situation or a physical situation that requires energy is endothermic. Heat energy must go in an endothermic situation. So to break the old bonds between solute particles and solvent particles that exist between themselves, it's going to require energy. So the first part of dissolving is the endothermic part of dissolving. And that's where we have to provide energy to break apart the old bonds. Now, less intuitive for most students to understand, but remember, we're talking about the exact opposite process. So hopefully it makes sense that the energy would be the opposite, would be what happens next. The solute and the solvent particles are now going to come together and form a new bond that didn't exist before. Now, when you form bonds, and this is not as intuitive, but remember, it's the opposite, so the opposite better happen with energy. When you form bonds between particles, they go to lower potential energy. That means their energy is dropping. It's losing energy. Well, that energy is going to go to the surroundings. So when particles of solute and solvent come together to form new bonds, that's going to release energy, and we call that exothermic. So all dissolving involves the endothermic part, where we have to break the old bonds, and the exothermic part, where we make new bonds. And overall, who wins is going to determine whether the heat of solution is endothermic or exothermic overall. So the overall energy change that takes place is what's going to determine our heat of solutions. Because in some situations, it's going to actually involve more energy to break the old bonds than gets released when we make new bonds. And in that case, we're going to end up with an overall endothermic situation. And that's what happens with a chemical cold pack. With chemical cold packs, we're dissolving typically some sort of nitrate, like potassium nitrate, in water, and or calcium nitrate. And when it dissolves in water, it needs energy. And yes, it's going to release some energy when the water hydrates and forms an attraction to the ions, but it's not near as much that was required to break apart the old bonds. So overall, it's going to get cold. It's going to need energy. It takes that energy from the surroundings, and as it's stealing energy from the surroundings, you feel cold. So in a chemical cold press, you're dissolving something in water, and it requires energy because the bond breaking part is bigger. Now, in a chemical hot pack, you're also talking about dissolving two things together. But in this particular case, the bond making part releases more energy than the bond breaking part required. And therefore, in the hot compress here, it's going to get warm. And that's once again because the exothermic making part was bigger than the endothermic breaking part. And different substances have different energies involved. So sometimes you end up overall endothermic, sometimes you end up overall exothermic. A good example of an exothermic thing is related to a lab safety idea. When we're mixing acids with water, We always add the acid to the water and never the water to the acid. The reason is dissolving of acids, concentrated acids, it's always going to be exothermic. So it's going to involve a release of energy. And it's such a great release of energy that if you add water to the acid, the large amount of energy released can actually cause that little drop of water to boil, and it'll spatter that acid in the surroundings. So for safety reasons, we always try and add our acid to our water, never our water to our acid. Now, the last thing we're going to look at in the first set of notes here is what happens to water itself when you dissolve certain types of substances in it. All aqueous solutions, aqueous, remember, means dissolved in water, we talked about this earlier in the year, can be classified in terms of whether it makes the water conduct electricity or not. Because pure H2O, as a molecular substance, doesn't carry charge. So therefore, it's not a conductor of electricity. So when we have distilled water, it's a non-conductor. But when we dissolve ions in the water, which can carry charge, then it conducts. And any substance that makes water conduct electricity we refer to as an electrolyte. So when it dissolves in water, or actually when it's in its molten form, so as a solid it melts into its liquid form, because it's made up of ions, it can carry charge, and therefore as a liquid or dissolved in water, it's going to allow the water to conduct charge, and therefore it's an electrolyte. It makes the water conduct. On the flip side, molecular substances dissolved in water don't allow for the conduction of or movement of electrons because they don't have a charge to be attracted to and flow to make the electrons move. So non-electrolytes don't conduct electricity when they're in their aqueous or their molten form. Ionic compounds, when you dissolve in water, will cause it to conduct. So ionic compounds are always electrolytes. And molecular substances, on the other hand, like water itself, when they dissolve in water, like putting sucrose or table sugar in water, you can dump as much sugar in there as you want, but it's not going to make the water conduct electricity because pure water is going to look like this. Dump a non-electrolyte like a molecular substance in water, and it's still not going to make the light bulb light up. But if you put an ionic compound in water, that breaks apart into lots of ions, and it glows very, very brightly. Well, there are some types of ionic compounds. Weak acids would be an example of this, that only partially break apart and make ions. And those things are a weak conductor. So they're not a strong electrolyte. They're not a non-electrolyte. They're actually a weak electrolyte. So weak acids like vinegar don't ionize near as much in water as something like an ionic compound like sodium chloride would. So therefore, it is a weak electrolyte. Still an electrolyte, but it's not as strong of electrolyte as most ionic compounds are. And that ends our first notes over chapter 15 and 16.